Section 20.1 Crystal Field Theory. Subsection H Octahedral versus tetrahedral coordination. In an octahedral complex, the transition metal center forms 6 bonds with 6 ligands. Therefore, it's in general more favored energetically than a tetrahedral complex. In a tetrahedral complex, only 4 bonds are formed between the transition metal and the ligands. But of course, there are exceptions. When is the formation of a tetrahedral complex favored? Well, 3 different scenarios. 1. When the 4 ligands are really bulky, there's no room for this transition metal to be bonded to 2 more ligands. That's 1. 2. If the 4 ligands each has many lone pair electrons that repel each other, and then in this case, well, this transition metal center prefers to form only 4 ligands due to the strong repulsion between the lone pair electrons from the ligands. And 3, when the 4 ligands each form a double bond with the transition metal center, because a double bond, well, or a triple bond, but rarely you have a triple bond between the transition metal center and the ligand. So when a double bond is formed, it consists of 4 bonding electrons. So the repulsion between 2 double bonds is stronger than the repulsion between 2 single bonds. So in that case, you may have a tetrahedral complex. One example is permanganate or tetraoxidal manganate. It's just MnO4 with 1 negative charge. Now let's look at the ligand field stabilization energy for a octahedral complex versus a tetrahedral complex for their high spin electronic states. So this table is only for the high spin cases. And actually, if you have a high spin case, the first column you should look at is when you have 5 d electrons. Well, each of them will just occupy one of the 5 d orbitals. And all these 5 electrons will have the same spin. Well, they can all have the alpha spin, or they can have all beta spin. So that's the high spin cases. All right? And then in this case, well, this LFSE is just 0 for all cases. Well, it's simple. In the octahedral structure, you have 2 electrons occupying the Eg orbitals, 3 electrons occupying the T2G orbitals. So overall, the LFSE is 2 electrons times positive 0.6, and then 3 electrons times negative 0.4. So overall, the LFSE is just 0. All right. So, but if you have only 4 electrons, well, you can remove 1 electron from the Eg orbital, and then you have overall negative 0.6 delta O LFSE. What if you have 6 electrons? You have one more electron in the one of the lower energy T2G orbitals, and then delta O, you have additional negative 0.4 delta O, so etc. And this row tells you the amount of LFSE when you have between 0 and 10 d electrons. All right, so those are just the LFSE for the octahedral complex in the high spin electronic state. And similarly, we can have another row for the LFSE in a tetrahedral complex. But these numbers are not in delta O, they are in delta T, of course. So in this tetrahedral complex, you have the 2 doubly degenerate E orbitals below the barycenter and 3 T2 orbitals above the barycenter. So when you have only 1 d electron, it occupies one of the 2 doubly degenerate orbitals. The LFSE is negative 0.6 times delta T. And then we have 2 electrons there, just negative 0.6 times 2. when you have 3d electrons, well, because we're talking about the high spin electronic state, then you need to put one of the 3 electrons in the higher energy T2 orbitals. So you got negative 1.2 plus 0.4. That's why you got this number. And then you have 2 electrons in the higher energy orbital, 3 electrons in the higher energy orbital. That's why this delta T does not keep going up. It goes up and then goes down. And then it goes up and goes down. So that's why. And then delta T is roughly 44% or 4/9 of delta O. So we need to do a conversion here. So we convert this delta T to delta O. Basically, we multiply this row by 0.444, which is 4/9. And then we got a row of new numbers, all right, in delta O. And then we're going to just take a look at the difference between OH and TD. We'll just look at the difference in LFSE, ligand field stabilization energy. So we're going to use these numbers minus these numbers. All right, I made a mistake here. I shouldn't put this absolute sign here. So it's just this number minus this number, we have this number. This number minus this number, we have this number. This number minus this negative 1.2 minus this number, we get this. So I want you to pay attention to the 2 most negative numbers in this row, here and here. So what does that tell you? That tells you if your transition metal center has 3 d electrons or 8 d electrons, well, very likely it's going to be octahedral complex due to this very large negative ligand field stabilization energy in the octahedral complex in comparison with the tetrahedral. So big difference here. All right, there's a big difference here if you make this to comparison. All right, so what about other cases? Well, if you have D4 or D9, well, still I would choose octahedral over tetrahedral because negative 0.42, although it's smaller than 0.84, but it's still quite significant. Delta O, again, is roughly 20,000 wave numbers, plus minus 10K. So if you do a multiplication, 0.42 times 20,000 K wave numbers, it's still 8,000 wave numbers. That's, I think, roughly 1 electron volt. So 1 electron volt is about 96 kilojoule per mole. So it's still a significant difference between the LFSE in the octahedral structure and the LFSE in the tetrahedral structure. All right. So again, I want you to be able to do the unit conversion yourself on a piece of paper, or even better, in your head. But again, I mean, you can hopefully you can easily convert the wave numbers to electron volts, to kilojoule per mole, to kilocal per mole, etc. Okay, so those are the numbers. This is just a visualization of the LFSE in a tetrahedral structure. All right, it becomes 0 when you have 5 d electrons occupying the 5 different orbitals. All right, and the blue circles are the LFSE in the octahedral complex. All right, so you can see the biggest difference is here. When you have D3, look at the difference. It's huge. And then when you look at D8, huge difference. So if you have D3 or D8, well, choose octahedral. And what about D4 or D9? Well, more likely octahedral. Well, and we learned the Jahn-Teller effect. So if you have D9, well, it's going to be octahedral because in the D9 structure, the Jahn-Teller effect is also significant. The Jahn-Teller effect also effectively reduces the energy of this octahedral structure. So I would choose octahedral over tetrahedral when you have a D9 transition metal center. What about D4? Well, actually D4 is different from D9. In this case, we're talking about high spin D4, and then you'll see more significant Jahn-Teller effect. If you have a low spin D4, well, that's a different case. Low spin D4 has a much smaller Jahn-Teller effect in the octahedral complex. Alright, so even if it's distorted, it's going to be slightly distorted. The Jahn-Teller effect will reduce the total energy slightly. So I wouldn't put D4 and D9 in the same category. So D9 still, I would say, more likely, much more likely. Octahedral, D4, I'm not 100% sure. What about other cases? Well, some other cases, D1, D2, and then D6, D7. The difference is fairly small, and except, for the D7 case, you may observe Jahn-Teller effect when you have a low spin case. But again, this is a table for the high spin electronic state. So when you have a low spin electronic state, you need to recalculate this number. All right, it's just I want to remind you in this table, for simplicity, we only looked at the high spin cases. For example, over here, those LFSE is just 0. All right, and now let me give you a just example high spin cases. If you have a D7 high spin cases, the Jahn-Teller effect is minimal. Well, because again, if you have high spin D7, that means you first put 5 electrons in 5 different d orbitals, and then you put 2 more electrons in the lower energy triply degenerate T2G orbitals. So it's actually just DXZ and DYZ orbitals, and the Jahn-Teller effect is very small for T2G orbitals. It's much larger for the EG orbitals. All right, only because again, DYZ and DXZ are not pointing directly in the Z direction. Okay, so that's why. Now let's look at this case, Cobalt 2. Cobalt 2 plus is D7. So in this case, I think we're talking about high spin electronic state, because if you look at the ligands, those are weak field ligands. So it's going to be the high spin case. And if you look at high spin case, D7, the difference in LFSE is only 0.27. So in that case, well, the octahedral structure is not much favored in terms of LFSE. And also chlorine minus, bromine minus, iodine minus. Each of them has 4 lone pairs, and only 1 lone pair is used to make a bond. So they have 3 other lone pairs, and those lone pair electrons repel each other significantly. So that's why this Cobalt 2 does not like to form 6 bonds with those halides. They form only 4 bonds with those halides. So it's going to be, I think, tetrachlorido, bromido, or iodido, cobaltate, because overall the charge is going to be -2. You have 4 negative charges on the 4 chloridos, and then you have +2 charges on the cobalt transition metal center. So it's cobaltate in the end.